This is Stephen Hawking's book, The Theory of Everything, The Origin and Fate of the Universe. As long as 340 BC, Aristotle, in his book On the Heavens, was able to put forward two good arguments for believing that the earth was a round ball rather than a flat plate. First, he realized that eclipses of the moon were caused by the earth coming between the sun and the moon. The earth's shadow on the moon was always round, which would be true only if the earth was spherical. If the earth had been a flat disk, the shadow would have been elongated and elliptical, unless the ellipse always occurred at a time when the sun was directly above the center of the disk. Second, the Greeks knew from their travels that the pole star appeared lower in the sky when viewed in the south than it did in more northerly regions. From the difference in the apparent position of the pole star in Egypt and Greece, Aristotle even quoted an estimate that the distance around the earth was 400,000 stadia. It is not known exactly what length the stadium was, but it might have been about 200 yards. This would make Aristotle's estimate about twice the currently accepted figure. The Greeks even had a third argument that the earth must be round, for why else does one see the sails of a ship coming over the horizon and only later see the hull? Aristotle thought that the earth was stationary and that the sun, moon, the planets, and the stars moved in circular orbits about the earth. He believed this was because he felt, for mystical reasons, that the earth was the center of the universe and that circular motion was the most perfect. This idea was elaborated by Ptolemy in the 1st century AD into a complete cosmological model. The earth stood at the center, surrounded by 8 spheres, which carried the moon, the sun, the stars, and the 5 planets known at that time: Mercury, Venus, Mars, Jupiter, and Saturn. The planets themselves moved on smaller circles attached to their respective spheres in order to account for their rather complicated observed paths in the sky. The outermost sphere carried the so-called fixed stars, which always stay in the same positions relative to each other, but which rotate together across the sky. What lay beyond the last sphere was never made very clear, but it certainly was not part of mankind's observable universe. Ptolemy's model provided a reasonably accurate system for predicting the positions of heavenly bodies in the sky. But in order to predict these positions correctly, Ptolemy had to make an assumption that the moon followed a path that sometimes brought it twice as close to the earth as at other times. And that meant the moon had to sometimes to appear twice as big as it usually does. Ptolemy was aware of this flaw, but nevertheless his model was generally, although not universally, accepted. It was adopted by the Christian Church as the picture of the universe that was in accordance with Scripture. It had the great advantage that it left lots of room outside the sphere of fixed stars for heaven and hell. A much simpler model, however, was proposed in 1514 by a Polish priest, Nicholas Copernicus.
Nicolaus.
Okay. At first, for fear of being accused of heresy, Copernicus published his model anonymously. His idea was that the sun was stationary at the center and that the earth and the planets moved in circular orbits around the sun. Sadly for Copernicus, nearly a century passed before this idea was to be taken seriously. Then two astronomers, the German Johannes Kepler and the Italian Galileo Galilei, started publicly to support the Copernican theory. Despite the fact that the orbits it predicted did not quite match the ones observed. The death of the Aristotelian Ptolemaic theory came in 1609. In that year, Galileo started observing the night sky with a telescope which had just been invented. When he looked at the planet Jupiter, Galileo found that it was accompanied by several small satellites or moons which orbited around it. This implied that everything did not have to orbit directly around the Earth as Aristotle and Ptolemy had thought. It was, of course, still possible to believe that Earth was stationary at the center of the universe, but that the moons of Jupiter moved on extremely complicated paths around Earth, giving the appearance that they orbited Jupiter. However, Copernicus's theory was much simpler. At the same time, Kepler had modified Copernicus's theory, suggesting that the planets move not in circles but in ellipses. The predictions now finally match the observations. As far as Kepler was concerned, elliptical orbits were merely an ad hoc hypothesis, and a rather repugnant one at that, because ellipses were clearly less perfect than circles. Having discovered, almost by accident, that elliptical orbits fitted the observations well, he could not reconcile with his idea that the planets were made to orbit the sun by magnetic forces. I have no clue, this is my own addition, I have no clue why magnetic forces came into this thing over here. Magnetism has not been discussed in this chapter so far, so this is my own editorial here. I have absolutely no understanding why magnetic forces came into picture over here, and why it would result in elliptical orbits. Nevertheless, we can go ahead, it's not very important, I think. An explanation was provided only much later in 1687, when Newton published his Principia Mathematica Naturalis Causae. This was probably the most important single work ever published in the physical sciences. In it, Newton not only put forward a theory of how bodies moved in space and time, but he also developed the mathematics necessary to analyze those motions. In addition, Newton postulated a law of universal gravitation. This said that each body in the universe was attracted towards every other body by a force which was stronger the more massive the bodies and the closer they were to each other. It was the same force which caused object to fall to the ground. The story that Newton was hit on the head by an apple is almost certainly apocryphal. All Newton himself ever said was that the idea of gravity came to him as he sat in a contemplative mood and was occasioned by the fall of an apple. Newton went on to show that, according to his law, gravity causes the moon to move in an elliptical orbit around the sun and causes the earth and planets to follow elliptical paths around the sun. The Copernican model got rid of Ptolemy's celestial spheres, and with them the idea that the universe had a natural boundary. The fixed stars did not appear to change their relative positions as the earth went round the sun. It therefore became natural to suppose that the fixed stars were objects like our sun but much farther away. This raised a problem. Newton realized that, according to this theory of gravity, the stars should attract each other. So it seemed they could not remain essentially motionless. Would they not all fall together at some point? That's a scary thought. That's my own addition. Uh, in a letter in 1691 to Richard Bentley, another leading thinker of the day, Newton argued that this would indeed happen if there were only a finite number of stars. But he reasoned that if, on the other hand, there were an infinite number of stars distributed more or less uniformly over the infinite space, this would not happen because there would not be any central point for them to fall to. This argument is an instance of the pitfalls that one can encounter when one talks about infinity. In an infinite universe, every point can be regarded as the center because every point has an infinite number of stars on each side of it. The correct approach, it was realized only much later, is to consider the finite situation in which the stars all fall in on each other. One then asks how things fall if one adds more stars roughly uniformly distributed outside this region. This is a little complicated, my own addition, but let's just go through it. So let me repeat this once again. The correct approach, it was realized only much later, is to consider the finite situation in which the stars all fall in on each other. One then asks how things change if one adds more stars roughly uniformly distributed outside this region. According to Newton's laws, The extra stars would make no difference at all to the original ones, and so the stars would fall in just as fast. We can add as many stars as we like, but they will still always collapse in on themselves. We know now it is impossible to have an infinite static model of the universe in which gravity is always attractive.
Why is gravity attractive?
It's a good question with you because.
No, wait. Why is gravity attractive? Do you get what I mean?
தெரியாதுடா. I don't know. What do you mean? சரி, இந்த கிரேசி போசஸ் எல்லாம் வைக்காத. நான் ரெக்கார்ட் பண்ணிட்டு இருக்கேன், இதெல்லாம் வரும் ரெக்கார்டிங்கில். ஆமாம், என் பேர் கூட. It is an interesting reflection on the general climate of the thought before the 20th century that no one had suggested the universe was expanding or contracting. It was generally accepted that either the universe had existed forever in an unchanging state or that it had been created at a finite time in the past and more or less as we observe it today. In part, this might have been due to people's tendency to believe in eternal truths as well as the comfort they found in the thought that even though they may grow old and die, the universe is unchanging. Even those who realized that Newton's theory of gravity showed that the universe could not be static did not think to suggest that it might be expanding. Instead, they attempted to modify the theory by making the gravitational force repulsive at very large distances. This did not significantly affect their predictions of the motions of planets, but it would allow an infinite distributions of stars to remain in equilibrium, with the attractive forces between nearby stars being balanced by the repulsive force from those farther away. However, we now believe such an equilibrium would be unstable. If the stars in some region got only slightly near each other, the attractive forces between them would become stronger and would dominate over the repulsive forces. This would mean that the stars would continue to fall towards each other. On the other hand, if the stars got a bit farther away from each other, the repulsive forces would dominate and drive them farther apart. Another objection to the infinite static universe is normally ascribed to the German philosopher Heinrich Olbers. In fact, various contemporaries of பைத்தியம் சிரிக்காதடா அந்த மாதிரி, இதெல்லாம் ரெக்கார்ட் ஆகிட்டு இருக்கு. In fact, various contemporaries of Newton had raised the problem, and the Olbers article of 1823 was not even the first to contain plausible arguments on this subject. It was, however, the first to be widely noted. The difficulty is that in an infinite static universe, nearly every line or side would end on the surface of a star. Thus, one would expect that the whole sky would be as bright as the sun even at night. Olbers' counter-argument was that the light from distant stars would be dimmed by absorption by the intervening matter. However, if that happened, the intervening matter would eventually heat up until it glowed as brightly as the stars. This is very interesting. The only way of avoiding the conclusion that the whole of the night sky should be as bright as the surface of the sun would be if the stars had not been shining forever but had turned on at some finite point time in the past. In that case, the absorbing matter might not have heated up yet, or the light from the distant stars might not have reached us. And that brings us to the question of what could have caused it to turn up in the first place. The beginning of the universe. That is the next section in this chapter, which I will continue at a later time. Bye.